Good afternoon, my name is Suraj. I'm a tutor for Data 8, and today we will be going through the Spring 2017 midterm for Data Science 8 here at Berkeley. So now if you're watching this video, the expectation is that you've either done the Spring 2017 midterm that is, in class, or you've done the practice, and you're watching this, to figure out some of the questions that you were stumped on. And hopefully this will be a useful learning resource for you. So this midterm had 4 problems. Let's go ahead and get into problem number 1, which is focused primarily on Python expressions and making sure you know how to use functions and methods in the data science package and the NumPy package, right? So the first question gives us a table with columns department, name, role, and salary, pretty self-explanatory, and it wants us to fill in the blanks to complete the expressions. So the first problem, 1A, is we want to find the total salary amount paid to all faculty, right? So here we have a column titled salary, right? And we can imagine each row consists of the data for one either professor, or associate professor, or lecturer. So each row is for one staff member, right? So if we were to somehow add up all the salary values we have, so add up all of the 2,059 values we had for salary, we would get the total amount of money that is being paid to all people who are working at Berkeley as either a lecturer, professor, associate professor, or whatever, right? So then now we have to think, what are some ways we know how to sum things? Well, the sum function does a pretty good job of that, right? So what do we want to sum? Well, we want to sum a specific column of the table pay, right? So to do that, we can do pay.column. And now we have 2 choices. We could either put the number 3, which is the index of the column, right? Because this is column 0, this is column 1, this is column 2, and this is column 3. Or to be a little more direct, we can put column salary, which, is a little more readable because it tells us directly, okay, hey, take the column salary from the table pay and find the sum of that. And that's problem A. So B asks us to find the name of the 3rd highest paid faculty member, right? And so an important distinction to make here is that we don't want to find the amount of money that person was paid. We just want to find their name, right? We don't care about the amount of money they had, right? So in any question where we want to find the nth highest paid or the nth lowest paid or the nth anything related to some sort of rank, we always want to sort our table by some sort of metric first, and then it'll be easy to get a certain index, right? So here we want to sort by how much they're being paid, so it might make sense to sort by the column salary, right? And so this is just typical data science package syntax, .sort. So first we specify the column name, so again that's salary, and then next we have descending, which is a flag that is either true or false right now. So if descending is true, we're going to start off with the greatest salary value and move down, and then the last index, like the index 2059 minus 1, will contain the value of the lowest paid faculty member, and 0 will contain the value of the highest paid faculty member, which seems like something we want, right? Because our question is asking us to find one of the highest paid faculty members, right? So it'd be easier for us if the highest paid faculty member was at index 0. So you want descending to be equal to true because we're going to be dealing with the higher values, right? So now we have a column so now we have the same table where everything's sorted by the values in salary. Well, like we said, we don't care about the actual salary values. All we want is the name of the faculty member, right? So what we can do is just take the column name. Equivalently, instead of quote name, we could have written just 1 because we want the first column. And now we need to find .item something, right? Well, we want the 3rd highest paid faculty member, right? And we know in Python we start counting at the number 0. So 0 would correspond to the 1st highest paid faculty member. 1 would correspond to the 2nd highest paid. And then similarly, 2 would correspond to the 3rd highest paid faculty member. So this line right here will give us the name of the 3rd highest paid faculty member. And to recap what we did, we sorted this entire table by salary from greatest salary to least, took just the column names, so we're going to chop this down from a table to being an array, and then we're going to take just item number 2 of that, right? So now we're dropped down just to a string, right? So it's important to see what our data structures are at each of these steps. Okay, so problem C, we want to find the number of lecturers in the department that has the most lecturers, assuming that one department has more lecturers than the rest. Right? So thinking back to our experiences in homeworks and whatnot, what Python function did we always use to find out the number of instances of a certain column, right? If you get what I'm getting at, that was group, right? Group by default, when we specified a column name, it would tell us the number of times that any of the rows belong to that type of column, right? So we know that group might be something we want to use here, right? And what exactly are we grouping, right? We want to find the number of lecturers in each department, right? And once we have some sort of representation of the number of lecturers in each department, well, we can just take the max of that, right? Which is already being told to us here. Right? We're going to be taking the max of some column count, and that will tell us the number of lecturers in the department that has the most lecturers, right? So we already know that we're going to be taking the max of something. We're going to be taking a column count. So we know that whatever is enclosed in these square brackets must be a table, right? Because to be able to take a column away from it, or to be able to select a column from it, it must be a table, right? So this can't be an array or another column or something like that, right? So whatever's in here must be some sort of table, right? So well, first we just want to pay the values of pay where they're only lecturers, right? Like we don't really care about associate professors or professors in this question, right? So here is a simple dot where the department is equal to, where the role is equal to lecture, right? All we care about is lecturers in this case, right? So we can just do pay dot where role is equal to lecture, and now what we want to do is group it by department, right? So now we'll have a list that looks something like department, lecture count, and then we'll have our departments from above, journalism, econ, south and southeast Asian studies, and we'll have the number of lectures like 10, 5, 7, or whatever the values are, right? So this is the kind of table we're going to have here, right? So then dot column count was just going to take this column here, which will just have all the numbers of lectures that each of the departments have, and if we take the max of that, that will tell us the number of lecturers in the department that has the most lecturers, right? It's not going to tell us the department name because we're just taking the column count, right? We're not keeping track of the department as well. We're just going to find the number of lecturers in the department that has the most lecturers. So that's kind of how we approach problem C. Now problem D, we want to find the average faculty salary after all faculty members get a 10% raise each year for 3 years, right? So one thing to notice here is that if all faculty members, if we have some sort of function that can go through and to each number in salary, we are able to transform it to its new salary value in 3 years from now. That's equivalent, and then taking the average then, that's equivalent to averaging them now and then applying the transformation that will give us the new salary values 3 years in advance. So what that means is, if I take the average salary now and bring that 3 years into the future, that's equivalent to taking the average salary now, that's equivalent to taking each individual salary 3 years into the future and then averaging them. So what we're going to do for this question is find the current average salary and then find how we can compute what the average salary will be in 3 years, as opposed to individually computing what each salary will be and then averaging those. So hopefully that distinction is clear. Both will give you the same answer, but this is much, much quicker because clearly here we only have one line to solve this question, right? So how can we find the average of all the salaries that are being given out, right? Well, that's pretty simple. We just want to find the average of the column salary, right? So we have np.average, which will give us the average of any column, and then we just need to specify which column. So that would be pay.column salary. So this will give us the average salary value of all of the faculty members right now. So now how do we transform this 3 years into the future, we ask, right? Well, this is just a formula we're accustomed to from lecture, right? If we're increasing something by some given percent value for a certain period of time, well, we just multiply it by 1 plus the percentage increase exponentiated to the time period, right? So here, we're getting a 10% raise each year. So 10%, that's equal to 10 out of 100, or 1 out of 10, or 0.1. So I'll write this as 1 plus 0.1. And we're doing this 3 years, right? So after the first year, they'll get a 10% increase, and then after the second year, another 10% increase, and then after the third year, another 10% increase, right? So we have three 10% increases, which simplifies to 1 plus 0.1 to the exponent 3, right? And now we need to write this in a way that Python can actually solve it, right? So I mean, we could leave it as 1 plus 0.1, but it's a little easier if we have 1.1. And then, of course, Python has no way of, doing exponents like that. So we'll do 1.1 star star 3, right? So this here will be the scalar factor, which will increase the value in the current year to 3 years in the future, if in every year each employee gets a 10% raise for 3 straight years. So this will be the solution to part D. And lastly, we have part E. As you can see, I started to kind of work on it a little bit down here. But what it tells us is the table big created below only contains rows for faculty and departments that have both lecturers and professors, right? So you can see here it's possible for some departments to only have associate professors, right? Like we can imagine a case where that happens. Or for some reason a department only has professors and not lecturers, right? And I'm underlining them here because these are the words we see, not necessarily indicative of what these departments have, right? So what we want to find is the minimum pay gap for any department, right? And what that is the minimum absolute difference between a department's lecturer salary and its professor salary, right? So first we have to ask ourselves, what does the big table already have, right? Well, first we have to understand, what does pivot do, right? So pivot, the first argument in pivot specifies what the titles of our columns should be, right? So role, well, we only have a couple different types of roles, right? Well, we'll have lecturer, we'll have prof, have associate prof, and then the second argument in pivot will be the title for all of our rows, right? So then we'll have journalism, econ, South and Southeast Asian studies, right? And so on. So that's what our has lecturer table will look like, right? And then what it's going to do is take has lecturer where there's at least one lecture recorded, right? So by default, pivot will do exactly what group does and just tell you the number of lecturers in journalism, or the number of associate professors in econ, right? So what we're going to do, we're going to have some values here, and what we're going to do is get rid of all the non-zero values for lecturer, right? And then has both will do the same thing for professor, right? So it's going to say, okay, we already have all the non-zero, we already have all the departments that have at least one lecturer. Now give me all the values that have at least, all the departments actually, that have at least one professor as well. So then big is going to be a list, big will be a subset of our pay table, but it'll have only the departments that have at least one lecturer and at least one professor. So big will look something like this, but it'll only contain values from departments that have at least one lecturer and one professor, right? So how do we go about finding the minimum pay gap for any department, right? So right here we have, like in the skeleton code that they give us, we have big dot something, and then something with 4 arguments, right? So, and then here we were subtracting away 2 different columns. So since they kind of use pivot here, we're kind of hinted to us that we also want to use pivot again, right? And why would using pivot be helpful, right? Like what could we use pivot to do, right? Well, if we had some sort of chart that looked kind of like this, right? Where we have the average salary of a lecturer here and an average salary of a professor here for any given department, that would be pretty useful, right? So pretend we had some value like A, the actual numbers are valued B, C, D, E, F, where A is the average salary paid to a journalism lecturer, B is the average salary paid to a journalism prof, F is the average value paid to a Southeast Asian Studies professor. If we were able to concoct some sort of table that looked like this, that would be great, right? Because we could just find the minimum difference between the average of this column and the average of this column, right? And that would give us our minimum value of our pay gap, right? So what we want to do is find, let's create a table that has the average salary of each of these positions, right? Average, salary for econ lecturer, average salary for journalism prof. Get some sort of table like that, and then take the average value for lecturers and average value of professors, subtract them, and find the minimum value of that. And that will give us our minimum pay gap, which is what the question wants us to find. Right? So, from what I already said, we're going to try and use pivot, right? And then, as we used up here, our first argument into pivot is what will generate the column names. And these, as you can see, are roles, right? Lecturer and professor are roles. So these should be role. And then here, this is the title of the second parameter into pivot. And then the second parameter to pivot is what will generate all of the row names. Right? So this will be department. Right? And now here is where we have to specify some non-default or non-required arguments into pivot. Right? So by default, what pivot will do is it won't give me the average salary value, but rather it'll tell me, okay, there are 10 journalism lecturers, there's 7 journalism profs, and so on and so forth, right? It'll just give me values for how many, it'll give me the count for how many things of these there are. It won't really tell me anything about the salary, right? Which is, we don't really care how many there are, we care about the salary, right? So the optional third argument into pivot is a column that we want data pulled from instead of the count, right? So now instead we will get the salary, but what we don't want is just the salary, we want the NP dot average of the salary. So what this will do is exactly what we wanted before. We want the average journalism lecturer salary, average econ professor salary, and this will populate our entire table with the average values for lecturers and professors from all these departments. And now we want the minimum pay gap for any department, right? Well, of course, if we want the minimum of something, our first term will be min, right? And now the pay gap is defined as the absolute difference between a department's average lecturer salary and professor salary, right? And we'd assume that a professor's salary is greater than a lecturer's salary, but there's no need to assume anything here because we're taking the absolute difference, right? But so that would imply that we would use mp.abs here. And then we just need to take the two columns, lecturer and professor, right? So here we'll take lecturer, here we'll take professor. It doesn't really matter in what order we take them because we're going to take the absolute value. So what this is going to do is take the average value for the column of lecturers, average value of the column of professors. It's going to subtract these off. So we'll get some difference here, some difference here, some difference here, some difference here, right? Because in data science and NP, if we subtract two arrays, pretend we have like C, comma, D, comma, E, and F, comma, G, comma, H, pretend these were equated to A and B. A minus B will give us, the pairwise sum of the, or pairwise difference of these, right? So what we'll do, if we're subtracting lecturer and professor and taking the average value of that, so what that's going to do for us is say, okay, here's the difference. Sorry, here's the absolute value of absolute difference between what a journalism lecturer and professor is paid. That's here. Here's the absolute difference between what a econ lecturer and econ professor is paid. That's here. And we'll get all those values. And as the question specifies, we want the minimum pay gap, so we'll just take the minimum of that, and that'll give us the minimum pay gap. And that wraps up question number 1. Okay, now we're moving on to question 2, the histogram question. So we get this histogram of mother's heights, father's heights, and son's heights. And then the question asks us to use our histogram knowledge to calculate certain values. Right, so the first question asks us, what is the percentage of mothers that are at least 60 inches but are less than 64 inches tall, right? And so we go ahead and look at our mother's histogram. We see we have a bin that includes 60 and 62, and we have a bin that includes 62 and 64, and we see that, okay, this is perfect. 60 and 64 are both endpoints of bins, so we can accurately describe the data in between them, so we can just use our the histogram formulas that we're used to. Since we know that this is a histogram, the area of all bars must be 100%. So since we want to calculate the area of these two bars inclusive, we just use our typical width times height. So for the first one, 60 to 62, we have 2, which is our width, which we can also write as 62 minus 60, times our height, which is clearly 6, which is 12%, right, because we have percent per inch. And 62 to 64, we have, well, again, 2 will be our width, and our height will be 14. So we add that up, and we will get 14 times 2, which is 28%. So our total should be 12 plus 28, which is 40%, which is the percentage of mothers that are at least 60 inches, but less than 64 inches tall. Cool. So 2 asks us the percentage of fathers that are at least 64 inches tall, but less than 67 inches tall. So we look at the bins that we have. We have a 64 for the father's side, but we see that 67 would actually lie halfway in between 66 and 68, right? And so it's tempting to say, okay, why don't we just half the bin size of 66 and 68 and just take half of this bin, right? But that's not how histograms work, and we don't accurately know how the data is spread out between the 66 and the 68 bin. So we can't accurately find the area or find the proportion of values that are in between 66 and 67 due to the nature of histograms. So this question, actually, the answer is unknown because we don't know the distribution of the values between 66 and 67 inches. Now the third question is also kind of similar. The number of sons that are at least 70 inches tall, and it's not because that we have weird bins. Here, obviously, we have a bin that starts with 70, and we can quickly find the proportion of sons that are at least 70 inches tall, right? We just add up this area, and this area, so we'd find the proportion, which is whatever, but nowhere are we given the actual number of sons, right? So we know that each family consists of one mother and one father, but they also consist of some varying number of adult sons. So nowhere are we told how many sons any one given family has, right? This is just some average value. So we're never told how many sons there actually exist in our sample size. So again, this value is unknown because we don't know how many sons there are total. So that's an important distinction to make. Here we can find the proportion of sons that are greater than 70 inches, but we don't know how many sons there are, so we can't find the number. And then part 4, the number of mothers that are at least 60 inches tall, right? So let's go ahead and look at our histogram here. At least 60 inches tall would be just subtracting off the area or the proportion of mothers that are less than 60 inches tall, right? And since we know we have 200 families, we know we have 200 mothers, right? So that's something we could write down, 200 mothers, right? And so we know we're going to have 100% of the mothers are at least 60 inches tall, except, well, for the mothers that aren't, right? And so the area of this bin is 2 times 2, which is 4%, right? Because 60 minus 58 is 2, and its height is 2, right? So 100% minus 2 times 2% times 200. So now we're being asked to find 96% of 200, which quickly we can find out to be 192, which is the number of mothers that are at least 60 inches tall. So to clarify, what we did was we said, okay, all the mothers here have a value that is at least 60, except for this one bar over here. So we can just subtract their area from 100% because we know the sum of all the values will be 100%. Alternatively, if you really had extra time in the exam, you could, find this area, 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 and find that area. But there's really no point because you'll find out that it adds up to 96%, which is what we found here. So the next question, part B, asks, if the father's histogram were redrawn, replacing the two bins from 72 to 74 and from 74 to 76 with one bin, what would be the height of that bar? And if it's impossible to tell, write unknown. So let's look a little bit at this histogram, right? So we see we have a bin from 72 to 74 and a bin from 74 to 76. And the question asks, if we had to replace this with some bin, with some bar, with a bin that was from 72 to 76, probably looks something like that, what would be the height of that bin, right? So it turns out that we can indeed find out the height, right? And so first, to find that height, we know the width of our new bin, right, which will be 76 minus 72, which is 4, which we can write down here, new width. 76 minus 72 is equal to 4. So first we want to find our current area, because we need the area of these two bars the sum of those two areas must be equal to the area of the 72 to 76 bar. Because again, histograms are based off proportion, so the sum of these two areas will tell you the proportion of values that are between 72 and 76 inches, and that must hold true even if we have one unified bin. Right, so currently we have one bin of area 2 times 6, and another bin of area 2 times 2, which will give us, we have 2 times 6 plus 2 times 2, well, that's equal to 16. So our current area is equal to 16, right? Because those are the areas of our current bins. And then again, that's from 2 times 4 plus 2 times 2. So we need our new height. Since we need the same area, we would take area divided by new width. So that will also be 4. So the new height is also 4 percentage units. And hopefully that's clear as to why. Again, what we did was we said, okay, since we're going to be spanning the same bar range, or sorry, the same bin range, the area of the bars must be equal. So the area of the two current bars we have must be equal to the area of the one new bar that we're adding in. And that's exactly what we did. And so now our last question with this histogram business is the percentage of sons that are taller than all the mothers is between blank and blank. Fill in the blanks in the previous sentence with the smallest range that can be determined from the histograms, and then explain your answer below. Right? So to do that, let's go ahead and take a look at our mother's histogram, and we see that the greatest bin in which we have values for the mother's category is 70 to 72, right? Which tells us that the tallest mother must be between 70 and 72 inches, right? So what we want to do is find the proportion of sons that are between 70 and 72 inches, which we can see, sorry, not by that bin, but by this bin here, right? So we want to find the proportion of sons that are taller than 70 inches and find the proportion of sons that are taller than 72 inches, and that will be the boundary that the question is asking for, right? So that requires us to find these three areas right here, which is not too difficult. So they all have a width of 2. The first one has a height of 14. The second has a height of 8, and I'm just reading these off of the graph. Third has a height of 2, right? So sons taller than 70 inches, that's just 2 times 14 plus 2 times 8 plus 2 times 2. Well, I can just add all these together at once, which would be 14 plus 8 plus 2, which is 24. That would be 24 times 2 is 48% of all the sons. And then now we want the sons that are just taller than 72 inches. Well, that will just lead us to exclude this bar over here. So we just want 8 plus 2 times 2, which would be 20%. So now what we have now is that 48% of all sons are taller than 70 inches, and 20% of all sons are taller than 72 inches. So then the percentage of sons that are taller than all of the mothers must be between 20% and 48%. Because, again, we know the tallest mother is contained somewhere in here. Okay, so now we're on number 3, the probability question. The first question asks us if we have 1 blue, 1 gold, 4 green, and 4 red tickets. If we draw 6 tickets uniformly at random with replacement, meaning that we're putting the tickets back as we select them, what's the chance that we draw at least one that is either blue or gold? So what's the chance that we draw one, like at least one that's blue or gold, right? And write our answer as a Python expression that computes the result exactly, meaning you can't do a simulation for this. You actually have to find an algebraic expression for this, right? So one thing we know by the total probability rule is that the sum of the probability of an event occurring plus the event not occurring, we could probably better write as this, event not occurring is equal to 1. So a basic example of that, the probability of the sun rising tomorrow plus the probability of the sun not rising tomorrow is equal to 1. While one of those options may be way more likely, just the sum of all possible outcomes in that question and in that consideration is 1. So similarly, with this question, either we get no tickets that are blue or gold, or we get at least one, right? Then the sum of those two events occurring will be 1. So the probability that we get 0 blue or gold tickets once we draw 6 tickets, plus the probability we get at least 1 blue or gold is equal to 1, right? Because that dichotomizes our sample space. We either get none or at least 1, right? So the reason I bring this up is because it's much easier to indirectly calculate this value by subtracting away the probability of getting 0 blue or gold from 1 than it is to calculate this value directly. So if you wanted to calculate this value directly, you'd have to consider the case where there's 1 blue and no gold, and then 0 blues and 1 gold, and then the various numbers of reds and greens you could have. But here, it's much easier. We're saying, okay, just take all the possibilities and subtract away the one case where there are no blues and no golds, and that'll give you the probability that at least one of your 6 cards is blue or gold. Right? So that's our setup for this question, and this has been repeated in the homeworks several times. Right, so we're going to have 1 minus the probability that none are blue or gold, right? So let's just take the case where we're picking one card, not 6, but just 1, right? We have 1 blue, 1 gold, 4 green, and 4 red. So if we draw a card at random, what's the probability that it's not blue or gold? Right? Well, there's 10 cards in total, and how many are not blue or gold, right? Well, there's 4 green, and there's 4 red. That adds up to 8 over 10, or 0.8, right? Excuse me. So if we draw one card at random, there's a 0.8 chance that it's not blue or not gold, right? So there's a 0.8 chance that it's either green or red. So we know we're going to have a 0.8 somewhere here. But we're not just drawing one card in this case. We're actually drawing 6, right? So we have to consider, okay, well, there's a 0.8 chance that the first one is not blue or gold. And for the second card, there's also a 0.8 chance that they're not blue or gold. And for the third card, there's also a 0.8 chance that it's not blue or gold. And since these events are conditional, because we're multiplying the probability of the second one not being blue or gold, given that we already know the first one is not blue and gold, here the probability doesn't change because they're independent. But this is still a multiplication rule question. We have the first card, the second card, the third card, and so on. Since we have 6 cards, that's going to be end up being 0.8 to the 6, right? We have to multiply by 0.8 for each of the 6 cards that we have, right? And since we want a Python expression that will represent this, we will have 1 minus 0.8 star star to the 6. And then we can go ahead and get rid of that. So this will be our answer. 1 minus 0.8 to the exponent 6, because for each of our 6 cards, there's a 0.8 chance that it's not blue or gold. So we want the probability that all 6 cards, of all 6 draws, none of them are blue or gold. So we have to exponentiate that. And then we actually want all the outcomes other than that, right? So we want all the outcomes where at least one of the cards are blue and gold. So we're going to subtract away the cases where none were blue and gold. And so this would be our final answer here. So next, we have a simulation question, and we are asked to define the function roll, which takes in parameters k and in trials, where k is the threshold at which we count the values, n is the number of fair six-sided die we're going to roll, and trials are the number of trials we're going to do. So essentially what this question means is if, for example, if k is 5 and n is 3, we're going to roll a six-sided dice 3 times. And we're going to count the number of times the value we get is either 5 or 6. Right? So here it's saying if k is 5 and n is 3, and we roll a dice, we get a 6, 4, and a 5. Right? Well, a 6, well, yeah, that's greater than 5. Greater than or equal to 5. A 4, that's not greater than or equal to 5. And 5, that is greater than or equal to 5. So in that case, the value that we're going to record is 2. And that's the value we're going to append to our outcomes, right? So we're interested in the number of times, or the number of times we get a value that is greater than or equal to k. And we're going to repeat that process trials times, and then, get into some sort of a histogram about that. But that's the second part of the question. Right, so our possible results, what are the possible results when we roll a die? Well, that's just np.a range 1, 7, which will give us the array 1, 2, 3, 4, 5, 6. Because as you remember, in Python, we always include the first index, but exclude the last index, right? So this will give us an array equivalent to 1, 2, 3, 4, 5, 6, which are the possible values when we roll a die. So for I and np.a range trials, meaning repeat this following block trials times, 5,000, 50, 10,000, whatever it is, rolls is going to be np.random choice possible results, comma, well, what's this asking us? This is asking us how many times do we want to roll this die, right? And so going back to our example, if n was 3, we took 3 results of the die, right? We rolled it once, we got a 6, we rolled it again, we got a 4, rolled it again, we got a 5, right? So we had to roll it n times. So what we want to do is n times randomly pick a result, 1, 2, 3, 4, 5, or 6, right? And so now what we want to do is keep track of the number of times the results we get are greater than k, right? So outcomes, well, when we look at the function np.append, its first argument must be the function that that already has all the data that we want, right? So this doesn't work the same way regular Python append does. np.append combines 2 lists. And since outcomes already contains all the data that we already have, all we need to do is append the new values we want onto outcomes, right? And so what we want to append onto outcomes is the number of times that our rolls was greater than or equal to k, right? Greater than or equal to k. Right, so we know rolls is going to take on some form. So pretend we have k is equal to 5, n is equal to 4. Well, our rolls array has nothing to do with k, right? It's just going to generate random numbers n times from the list 1 to 6, right? So it could look something like 3, 6, 5, 2, 4, 1, right? And that would obviously be with n is equal to 6. And the outcomes, we're going to go through and say, okay, pretend k is, in this case, 4. We're going to count the number of times that the values in rolls are greater than or equal to 4. So 6, yeah, that's greater than or equal to 4. 5, yep, that's greater than or equal to 4. 4, yep, that's greater than or equal to 4. So what outcomes is going to take on now? It's going to take on on its first iteration at least, it's going to take on the value 3. And then we roll this again, we'll get some new value for this, and we'll have some new tally. Then outcomes will become 3, comma, some other value, like 5 or something. And so on and so forth. And then by the end, outcomes will be a list that is as long as trials, and it will have the number of times that each of those trials had rolls that exceeded or equaled k. So hopefully that's clear what exactly this code block is doing. And at the end, we'll create a table of our outcomes. So then again, outcomes will have the number of times that once we roll the die n times, the number of times that we were greater than or equal to k, and then it will create a histogram for us, right? So hopefully that's clear. So part C, for each of the histograms below, circle the letter of the expression that generated it, assuming the roll is implemented correctly above. Right? So when we roll a die 30 times, right, we know that roughly since there's a 1/6 probability of each of each of the number of pips occurring, if you roll it 30 times, we'd expect on average to see 5 of each type of thing, right? We'd expect to see, 5 ones, 5 twos, 5 threes, 5 fours, 5 fives, and 5 sixes. And of course, if our number of trials is low, so for example 50, this is highly unlikely to occur, but the more trials we have, the more likely it is that our empirical distribution will approach the theoretical distribution, which would be what I have outlined here, right? So we're rolling a dice 30 times. We'd expect 1/6 of the time it'll be 1, 1/6 of the time it'll be 2, 1/6 of the time it'll be 3, and so on, right? So why is that useful? Well, here we'd expect 1/6 of the time the dice should take on the value 6, right? And 1/6 of 30 is 5. And so if you look at the case we have here, 1/6 of the time of 30 is just 5, right? And here all of our values are 30. So we'd expect if our k is 6, or we're looking for the number of times the dice is equal to or greater than 6, or just equal to 6, we'd expect that if we're going to roll the dice 30 times, it's going to happen 5 times. And what do we have here? Our histogram is centered around 5, right? So on the contrary, if we were looking at 4, then we'd want the number of times the die hit 4, 5, or 6, which is actually half of the die, right? So there's a 1/6 probability of hitting a 4, 1/6 of hitting a 5, and 1/6 of hitting a 6. That would actually amount to a half, right? So then actually 30 times a half is about 15. So we'd expect 15 times that our dice would equal or be greater than 4, right? But actually, in this case, our distribution is centered around 5, which would lead us to believe that our k wasn't 4, but it was 6, because we're centered around, we really only have one value, which is 6. So 30 over 5, 30 over 6 is 5, and we only have one value here. So we know it's either going to be B or D by that logic. And then the way to figure out if it's B or D is to look at the tail end behavior, actually, right? So if we were only going to run this 50 times, the chances of finding an outcome where we actually get 13 sixes or like 2 sixes is actually very, very low, right? As the number of times we run our trials increases, then the chances of getting these outliers, so for example, 13 sixes or no sixes, the probabilities of those events occurring increases. But since we're only doing 50 trials, the chances of that happening are very slim. As opposed to, if we look at this graph, here there's no tail end behavior, right? It's all kind of concentrated in between like 12 and 22, which leads us to believe no outliers were hit, implying that, maybe we didn't do 5,000 trials, and instead here, we only did 50, right? So you kind of have to do these questions in conjunction and reason them together, right? So what can we see about the right-hand side question? Well, it's actually centered around 15. And before I said, well, there's a 50% probability of getting either a 4, 5, or 6, right? So if we're going to roll a dice 30 times, we'd expect to see about 15 of them be the successful outcome we want. And we see on the right side here, we're centered around 15. So there we can take out the options 6 and 6. And then, like I said, there's no real tail end behavior here. Everything's kind of centered around what we would expect. So here we can say that this answer is C, whereas here we have values on the tails, right? We have values greater than 11 or 12, and it's very rare that if we're going to roll a die 30 times, we get 11 sixes, right? Like that, you can calculate the probability on your own, but the chances of that happening are very small, right? So here we have the tail end behavior, which leads us to believe we actually did this experiment several times in order to get those outliers, which would lead us to believe that this answer is B. So the final answer for these questions is B for part C, B for the first graph, and C for the second graph. And that wraps up number 3. Okay, so now we're on problem number 4, our hypothesis test question. So a recent paper called "Do Animals Bite More During a Full Moon?" analyzed 1,660 emergency room visits for animal bites. It shows bites by the day of the lunar cycle. And the lunar cycle, a full moon is on days 29, 30, and 1. And on all other days, the moon is not full. So here we have the data for several triplets, or rather all triplets of 3 adjacent days in the lunar cycle, and see you can see that here on 29, 30, and 1 the value is 268, whereas on all other days the value is significantly less. But so this question is asking us to find, okay, what's a null hypothesis for this question? If we want to go ahead and test whether or not there is something weird occurring with 29, 30, and 1, and then we'll go into that further in the latter part of the question. But so what's a null hypothesis? Well, again, a null hypothesis is something we currently believe to be true, right? We haven't yet proven that there's something special with the end of the lunar cycle with regards to animal bites. So we have to assume that since we're just picking a random 3-day sample, that the difference is occurring to chance, right? So the day of the lunar cycle on which an animal bites is drawn uniformly at random, right? Because we haven't really proved anything yet. All we're saying is, okay, we're just picking a random 3-day stretch in the lunar cycle, so the number of bites during those days must be chosen uniformly at random, right? So that the blank that an animal will bite on those days, so that the probability or chance that an animal will bite on days 29, 30, and 1 of the lunar cycle is blank. Well, it's telling us we want a number, right? Here we have 10 different bins, right? 17 to 19, 20 to 22, and so on, right? And 29, 30, 1 is just one of these 10 bins, right? And each of these bins is just 3 days in the lunar cycle, right? So since we're starting off by believing everything's being chosen uniformly at random, we have no other choice but to say that this is 1/10 or 0.1. And then, as always, any deviation from this proportion is due to random chance. So this is a quite typical hypothesis test setup. Any deviation from this proportion is due to random chance, and we're just starting off by believing what the numbers tell us, right? Like we can't assume anything that we haven't proven. Okay? So then part B tells us the histogram below shows the empirical distribution of a test statistic under the null hypothesis. And it's important to remember, what does empirical mean? Well, empirical means we go out and collect data, or we run a simulation, and these are the values we get, right? So empirical is the opposite of theoretical data, right? It was generated by repeating the following process 1,000 times. The lunar day for each of the 1660 simulated animal bites is chosen at random from 1 to 30, right? And then a test statistic was computed for each of the resulting 1660 days, the absolute value between 1/10 and the proportion of bites on days 29, 30, and 1. Right? So if we go back up here, we know that in our test statistic, 268 out of 1,660 of the bites fell into the range 29, 30, 1. Right? And here we have the empirical distribution of the test statistics saying, okay, this is how far you should be from the average of 1/10, right? So typically, at most, you should be 0.1 away, so you have 11% of the values will fall into a certain bin, or max 12, right? We see that or 12 or 8 rather, right? We see that no values are really more than 0.2 away from 1/10, meaning that the number of values in a bin should be about in this interval, right? But then if we go ahead and calculate the absolute difference between 1/10 and the test statistic, right? We'd have 0.161 minus 1/10, which is 0.1, which would be 0.061. Which if you look on this graph here, that kind of value is nowhere to be found, right? We see that the majority of the data we see is less than 0.02 away from the mean that we just determined 1/10, right? But here we have a value that is 0.061 away from it, meaning that our test statistic was so far away from what the null hypothesis was, meaning that we have to change something about the beliefs that we had, because this result is making us look further into our data, right? So what can we conclude? We reject the null hypothesis because the observed value of the test statistic is, well, it's the observed value of the test statistic is again the proportion of the values that fell into that bin minus a tenth, which and our tenth was our theoretical mean, right, which is 0.061, which is inconsistent with with the null distribution. What that means is inconsistent is that that kind of value does not appear in the empirical distribution, meaning that okay, there's something weird going on here. Our null hypothesis can't be true because the test statistic was so far away from the values that we determined with our simulation. And that just about wraps up problem number 4.